We're now going to have a run through the Hermes Voxel dosimetry software and hybrid reconstruction and organ dosimetry software as well, to give you a good flavor of some of the tools that the previous speakers have been referring to. And Helen McMeekin is going to help us with this. So Helena, if you'd like to show your screen.
Thank you very much, Steve. Okay, are you seeing the launchpad?
Yes, I am.
Are you seeing me?
Yes, I am.
Okay, great. Here we go. So let's look at Symmetry Software. So you've already had a bit of a flavor of this from Lara and from Will in the previous talk, but I will go through how it looks to actually click in the application and use it. So let's start out as if we're doing a post-lutetium therapy quantitative SPECT, first of all, and then we'll go on to do dosimetry on the SPECTs that we've just done. So first of all, we're going to use our hybrid reconstruction software. I hope that quite a few of you are familiar with this already. There's a mode now where you can ask it to show you what is being loaded into the application for the energy windows. Just got one here, and you can then select what you wanted from a set of input energy windows. So we're looking here at a post-lutetium therapy SPECT. So I can look, scroll through the projections in this tab, in this view. We're getting the sinogram at the location of this dotted line, and we can see the linogram there as well. If we want to, we can do automatic motion correction, Y direction, X and Y, or manual. So manual, if you can see a big chunk of sinogram, for example, that's off to the side, then you can bring these orange lines in, and then you can grab it and take it to where it should be in that way. So that can be a useful trick if you've got a patient who's suddenly jolted while they were having their scan. Also, just to very briefly mention a nice thing we've put in here, which is if you want to simulate a count study, for example, either due to reduced imaging time or reduced injection activity, you can do it here. So this is to add cross-on noise into your projection data before doing the reconstruction. Okay, I'm going to press right on to the reconstruction tab. So we already have our protocol loaded here. So clinically, you would just go on and click perform reconstruction. But all the juicy stuff, from the physics perspective anyway, is in this tab. So this is where I'm going to show you the reconstruction protocol that we're applying. And now, the great thing about Hermes and about this product is that it's really clear exactly what's being done. So you can switch off any of the corrections that you want, and you can modify them. And hopefully it's clear from the manual and also from the white paper of this application exactly how it's working and what it's doing to your data. So here is where we set the iterations and subsets for the iterative reconstruction. And here we have OSEM selected. So OSEM has been unchallenged for a long time in this field, but it's great to hear from Dan that they are investigating and clinically using now the Bayesian reconstruction. So all of these map options here are different Bayesian priors. For those people who don't know much about Bayesian reconstruction, essentially it's there is some prior information that you have. So all of these are different types of prior information. So some of them say that nearby voxels should be similar to each other. Some of them use the CT to guide how that similarity, how that smoothing is included in the image. And there's various other things as well, the kind of information that you can provide for the image that you're expecting to help with the reconstruction. So yeah, lots of stuff to experiment with here. But we will stick with good old OSEM for now. A nice little feature here, allow automatic parameter override. What this means is that Hybrid Recon will look in the DICOM header of your data for the collimator and manufacturer that was used to, of the camera that was used to acquire the data, and it will automatically populate the CT parameters here and also the resolution recovery. So I know in the past, people have had to have lots of different reconstructions for every different camera, every different collimator, but that's not needed anymore. We know the codes in the DICOM header for all of these things, and it will do this for you if you have this checked. It's a really nice option there. This is our list of ever-growing list of isotopes that we can deal with in hybrid recon. So for this one, we've chosen the upper energy window of lutetium. That's what we've got. Also, it can take the lower by itself. It can take, depending on how the camera presents it, because Hermes obviously doesn't make cameras, so we have to be able to deal with DICOM data from all the manufacturers. Some manufacturers present those two windows as a sum. So with average energy of 173, so we can take that as well, and we can take those two windows separately. We have here some new exciting isotopes, so holmium-166, which Jill touched on in her presentation. There's lots of interest in this on the European side, especially. Basically, as a replacement for yttrium-90 microspheres, holmium-166 is coming into that field. Got barium-133 as well here, quite recent, and various dual isotope pairs as well, some of which have that down scatter correction that David was talking about yesterday. Okay, let's move on. Also, we have this used GPU here. So hopefully most people have seen this by now who have hybrid recon, but the latest version of hybrid recon, the iterative algorithm is implemented now on the graphics card, on the GPU. It makes it significantly faster. So which you'll see when I set the recon going. We're doing attenuation correction based on a CT. We can use an internal or an external, just meaning a CT that was acquired simultaneously with the spec, or a CT that's brought from packs externally. And then there's steps where you can align that with the spec before doing the full reconstruction. So really nice flexibility there, meaning you can still use a CT to get this really good quantitation without having to have a spec CT scanner, which is a nice option. Resolution recovery. So this is just the standard Gaussian model of resolution recovery. It assumes perfect collimation, and it's just the model that as the patient gets further away from the camera, the resolution gets worse. So we can simulate the PSF, or the point spread function, at different distances and apply that to the data. That's applied as a convolution during the iterative loop. And that's why, so it was mentioned yesterday that the resolution recovery appears to smooth the data as well. And that's why the smoothing happens, because you get this convolution of the point spread function, which takes a lot of noise in the data as well. That's a kind of a side effect. We also have Monte Carlo modeling, so full collimator modeling. So this model up here, the Gaussian model, is good for when you have a well-collimated, well-behaved isotope like technetium or lutetium is pretty good as well, that we do here. But for others, so holmium, as Jill was talking about, I-123, I-131, and yttrium-90 are not so good. You've got lots of septal penetration, you've got scatter of the collimator septa, you've got absorption into the collimator septa, and then emission of a K-edge X-ray from the collimator, which is then detected. So these Monte Carlo models are the simulated point spread functions, including all of those effects. And actually, we can do these for your system. So I know lots of people prefer to, well, some people, lots is probably an overstatement, some people prefer to acquire yttrium-90 with medium energy collimators. So Antti, our developer, has kindly simulated the point spread functions for their systems as well with medium energies. So we're able to add on to here for your own personal system if it's not present yet. And with some good results. So you've seen the paper from Oxford there, looking at just the improvement you can get in that yttrium-90 image from the Bremsstrahlung spec, something that's reasonably useful for quantitation. It is pretty impressive, really, given how bad Bremsstrahlung looks by itself. Okay, let's just check now. Please type in any questions. I know there's lots of information here, but yeah, happy to take questions.
We do have a question already, actually, Helena.
Perfect. Yeah,
this is from Tahani again at Guys and St Thomas.
Hi, Tahani.
Question. She's saying, what is the SUV conversion factor that you've used? And I guess it'll be for the calibration factor, perhaps she's referring to in terms of
yes, yeah. So we'll be getting to that shortly.
Okay.
So this is the last tab, but I'm gonna keep moving through these tabs. We will get to that. So the scatter. So Hermes do Monte Carlo scatter correction only. We think that it's better in all circumstances than energy window-based subtraction. So what happens is that we take photons at this energy here, and we simulate them going through the new map that was created on this tab, and that's done as part of the iterative loop and subtracted in that way. That's why we do the scatter. And the SUV, so this factor, I'm not sure how correct this is, to be honest, because this is just for our demo. But the way that you would calculate this is just to do a uniform phantom scan with your own setup. So you'd have to have a known activity concentration in a uniform phantom. So just the uniform section of the Lima phantom would be fine. And then you can just make a straight calibration factor from that. So we have a calibration mode of this software, which allows you to put in the activity in your phantom, the volume of water in it, and then it can create that counts per second to megabec conversion, which is what's needed then as the last step to apply after all of these quantitative corrections have occurred. We're sure then that the activity distribution is accurate, and we are confident then to apply this to get voxel values in megabecquerels per mil, applying this. So I hope that answered your question, Tahani. Yeah, something that you would have to measure on your own system for your own setup. Okay. So let's crack on and do the reconstruction. So we're going to do close to 100 equivalent iterations here, and let's see how long it's going to take. So I'm going to hit perform reconstruction. All right, lovely warning. Thank you. Okay, this is a quick pre-reconstruction. That wasn't the whole thing. So what we're doing here is a quick check to make sure that the alignment is good. So even though we have done simultaneous spec CT, there could be a chance of patient motion between the CT and the spec field of view. So we want to make sure that hasn't happened, because two of our corrections, the scatter correction and attenuation correction, are based on the mu map. So that is really important quantitatively that that's well aligned. Now it's good, you can do corrections here if it's not, but I'm just going to continue here. So here it goes with its almost 100 iterations. Wow, so fast. So yeah, that's a really big improvement in time for doing those reconstructions now. But no time for a cup of tea.
No, and once again, that's because of our graphical. We use the GPU for to carry out these processes, so that's why we can do these things so quickly. Yeah, absolutely. Yeah.
So what we can do here is just put a label in if we want, and then just click save for it to go back to gold, or click hybrid viewer to launch it into our viewing application here. So if you wanted to further get an SUV an SUV result out of this, then you can put in, just as you would for PET, the activity that was injected and the patient weight as well, if you want to get a body weight scaling SUV. But you don't need to fill this in. The becquerels per mil unit is already there with the calibration factor. So that's enough. I just click hybrid viewer, you can have a look at it. Given a rather harsh window level, but yeah, so we're going to focus on it. Okay. There we go. So this is the reconstruction for this patient. Are we in a good position to carry on with the Voxel dosimetry now, Steve, or any more questions appeared?
No more questions have appeared, so I think we should crack on. Yeah.
Okay.
Great.
Lovely. Okay, tapping on. So what we're expecting, what the next application is going to look at is voxel dosimetry, and it's going to take in 3 time points of quantitative spec. So it's as if we've gone through what I just did after 3 times. So we've got maybe a 24-hour, 48-hour, and a 96-hour, for example, spec CT scan, or just a spec scan, because the same CT can be used for all of them if you'd like, post the therapy. So we've got 3 of those, we've reconstructed them, we've got voxel values in becquerels per mil. So it can take, as long as your voxel values are in becquerels per mil, it can take external reconstructed data as well. So if you have quantitative data directly from your scanners, this application, Voxel Symmetry, can deal with that as well, or PET as well, which obviously is natively in becquerels per mil. So it can take all of those things. I'm going to choose this as the reference one. Okay, thank you. So quite familiar scene from Lara's presentation. So what we're doing, the first step is to align these 3 time points. So we can choose, as Lara described, we can do a CT to CT alignment. So what we're looking at here is a little tricky to visualize this inside the application, but I've kind of got a sort of red version of the CT of the second time point floating over the first time point. So you can just try to match them up manually here, or just to make them unmatched again, we can rely on the registration algorithm, which is really good actually. So I'll probably do, it's your choice from a physics point of view as to which of these is better, CT to CT or spec to spec. I'm going to take the table down a little bit here so you can see it a bit more easily. So again, we've got both. We've got the second time point in red, underlying time point, first time point in white. Just set the full registration algorithm off on that. So that's it's just doing translation and rotation. It's not doing any deformation. So that's the second one to the first one. Now we choose the third one, full registration again. Let's apply that. It's doing the third one to the first one. Okay, lovely. So now we've got a set of 3 perfectly aligned post-therapy quantitative SPECT scans. We can do some dosimetry. So our imaging isotope, so we've got the choice here. We can set up a theranostic style calculation too in this application. So say we've done a diagnostic study based on I123 imaging, and we wanted to predict with exactly the same activity distribution what the dose would be if that were lutetium. We can set it up like this, and then we could also put in what was injected for imaging and what we plan to give for the therapy to see what we would get as a dose, then as a dose map output. So that's a really powerful thing, and hopefully will become more popular in future. There aren't many hospitals currently in the UK doing this, but it would be good to see it getting more popular. So let's say that we've got in here standard amount of lutetium. Like this, the time to first scan in this case is 24 hours. And let's just crack on with that. So I'm going to click calculate. So what's happening now is that it's doing, first of all, an integration at the voxel level, point by point. So okay, this is it's done. That's the dose map you're looking at now. But before I'm going to show you, I'm bring it in here, exactly what we've done in that calculation step. So what we can see is the first 2 steps of that workflow was to use hybrid Recon to do the quantitative reconstruction. The next steps that we did in Voxel Dosimetry were to line up the time points. Then we do these time activity curve calculations, dose simulations, then you get the dose map output. More detail here. So the cumulated activity, we do a trapezium rule integration for each voxel through all the time points. We use an instantaneous uptake assumption. So it kind of looks a little bit like this. We have, so at this point, a weakness in the software could be pointed out, that we don't do any kind of modeling here, that some people should say that you should fit a single exponential or bi-exponential model to better fit this time activity curve. And I think that might be the case at an organ level, but what our developer says is that at a voxel level, the noise level is so great that actually the smoothing, the regularization required to be able to fit that mathematically would lead to quite significant error because there's so much noise on voxel level that it just wouldn't be worth it to do that fitting. Also, mathematically, it's very time-consuming, resource-intensive for the algorithm to do that. So we haven't included that, and that's why. The dose that it's doing, so we're doing full Monte Carlo photon dosimetry. So this is the top level, kind of the gold standard of dosimetry, which is it's full Monte Carlo for the photons. So we simulate the photon interactions going through the CT until the energy gets less than 15 keV. We sample the XCOM photon cross-section database. So as the photons are traveling through the CT, we see what attenuation they're being subjected to, and then we simulate their interactions and the dose deposited, the energy deposited, which then calculated as a dose in each voxel. So electron dose calculation is more simple than that. We just use a local absorption model for electrons. So basically, the electrons are assumed to not travel outside their detection voxel. Now, this significantly speeds up the calculation, because if we did full Monte Carlo on the electrons as well, that's at the stage of the kind of research level Monte Carlo dose simulations. They take hours to run. Sometimes it's not really a clinically viable thing to do. And we found that with lutetium, the extra information here, the extra accuracy from including this is actually very small, because the electron mean path is much smaller than the size of the voxel. Now that assumption, or this validity theory, this was the subject of a PhD supervised by our developer, and that was validated for lutetium. Of course, for yttrium-90, which does have a slightly longer path length for the electrons, then that might be more of an approximation, but that's what it's doing. That's how we can manage to calculate these Monte Carlo photon, anyway, dose maps so quickly in a clinical setting. Again, happy for questions here. I'll try for questions anyway.
Yeah, please do. If you do have a question you think of, please do just enter it into the question panel at any time, and we'll pick it up.
Okay, so here is the dose map itself. So we're looking here at, so it's hybrid viewer fusion again that's showing this until Affinity can deal with it. So we're looking at a gray in every voxel now. So as I'm clicking around, hopefully you can see these small numbers changing here. We've got the window level is also specified in gray. So we've got 9.4 gray is the top. And then as I window down, we can see the levels of gray. So the amount of dose, absorbed dose in each of these voxels is represented directly here in the image. So let's do some regions. Let's put down this one. Let's go with a absolute. So let's do a 5 gray threshold. Going here. So reasonable tumor. And then, as has already been nicely shown by Lara, it's possible here to right-click and take a look at the doses as a table. So we output the minimum, the max, the mean gray, as well as standard deviation for those uncertainty calculations. Also, a couple of pre-stats here from the dose volume histogram to mimic what the kind of reporting that radiotherapy would do on their planned dose maps as well. And then that information also is represented in the dose volume histogram. You can get that inside the application, or you can just save the voxel values out to Excel and then pop it to yourself if you prefer. So yeah, that's the full workflow really for voxel dosimetry. You can spend some time here, as Lara showed, drawing volumes around the spleen or around the liver and transferring them over to here. To get those organ doses, as well as the kind of easier threshold dose for the lesions.
And as Johan has been alluding to previously, then the facility to process the three-dimensional dose maps will be available in the next version of Affinity as well. So actually, we do have a question. We do have a question now, Helena.
Great. Okay.
From David Hall from Bristol. Thank you, David. I don't know if you've got that on the screen, or I can read it out anyway. It says, given all the uncertainties mentioned earlier, should we be using lutetium dosimetry outside research centres and trials? Even if we can calculate a number, should we give it to clinicians?
Yeah, that's a really good question. I think as long as you can make an estimate of the kind of uncertainty that's present in your dose estimate, then yes. I think for me, it's better than nothing, because I know, I don't know if you've listened to Glenn Flux's talks on this. He's passionate about this, and often a comparison is made with radiotherapy and the kind of information that they present and the careful checking that they do. And compared with that, nuclear medicine therapy is kind of the Wild West, that we just go for it with the standard amounts, and what will be will be. So I think we really need to up our game. It's got to start somewhere. I think there's a lot of people are scared to give this because there is so much uncertainty, and the software is quite new and no one's really used to it yet, but we do have to get it going. It's not going to be perfect to start with, but it feels to me that something ideally with an uncertainty on it is better than nothing. So I would say yes, we do try to provide them with something.
I don't know if there are any further questions while we're on, but there's nothing currently in the panel there, Helena. So
okay.
Thank you very much for taking us through that. I don't know, did you want to take a look at the organ level dosimetry, or were you going to leave it there at that?
I don't mind, Steve. What have we got? How much time?
Well, we're kind of up to time, really. If we're gonna finish at 10:02, which we did say we would. So, and it's hard to get a poll on that at the moment. But perhaps we should spend a couple of minutes just having a look at it. If you've got a case there, we could show.
Yeah, absolutely. Whole launchpad. Okay. Let's do this one. So what we looked at just then was our Voxel dosimetry program, and there's the real advantages of that is that you can represent exactly what's going on in your patient, and you get the information at a voxel level. With this application, so this is the front end of our application, organ dosimetry. It's a hybrid viewer front end, and it works with Olinda in the background as the dose calculation engine. And Olinda, of course, uses the MERD model, which contains many assumptions, one of which is homogeneous activity distribution in the liver or in all organs. It can't represent, or at least in this program, it can't represent a voxel level. Only the mean dose is given, so you can't do that radiotherapy style dose volume histogram or D95% measurements, and also you don't use your patient's anatomy directly in it. You have to choose one of the models that's inside the software. So yeah, there's many drawbacks, but one of the positives is that you don't have to have quantitative imaging or quantitative specs at every time point. You can do it with planars as well. So here we have a set of planars. Again, we're doing post-lead cesium therapy. So actually we've got a bit of squash. We've got day 0, so quite close after administration, antigen post, day 1, antigen post, day 3, antigen post, day 5, antigen post. And I'll take this back down to 4 so that we can see what we're doing a bit more. We also have a spec CT that was acquired on day 1 over here, and we have on this view an overlaid view of the spec CT, kind of a pseudo planar spec CT that's in the orange, overlaid over the closest time point whole body. The reason for that will become clear later on. I'm going to try and whip through this. How much time do I have, Steve? Just to make sure that I'm going to get through it in time.
I was muted. Officially 2 minutes, but
2 minutes.
yeah,
Okay.
but you can go into my 5 because I'm not going to use them. So.
All right. Okay. Thank you. So first thing we can do here is the man with wobbly head. So what that's going to do is draw a sync on the whole bodies. So I hope you saw a little jiggle there. That one. So basically, it looked at all the whole body images and it tried to align them. The reason for that is that we can draw the organs on one time point and it will copy them across to the other ones. So if they're already well aligned, that will really help with that step. So let's go straight on to that now. Here is the whole organ list from Olinda. You do not have to draw all of these. Only draw the ones that you're interested in knowing the self-dose component to. So I'm going to choose the liver, and I'm going to choose this time point to draw it on because it looks quite nice here. Do this rough region there. Let's go with that. I'm also going to do a spleen. There we go. And this looks like a nice spleen here. So let's just grab that. Lovely. And then I think a left kidney and a right kidney as well. And maybe either this view for those. I'm sorry, these regions are not very good. I'm sure there's expert region drawers out there who are shocked. Oops, that was the left kidney again. Okay, let's do another one of those. Okay, choose the right kidney. There we go. Go down to here. And we do have some region drawing tools to help with this. In Hybrid Viewer, we have this tool here, which can do the kind of hot drag out. So let's put smooth on this. Let's choose Here, outwards. So this can get a nice total body region. We're doing this because we've imaged the patient here with a standard in the field of view. Otherwise, you wouldn't need to do a total body. You could just take the whole of the program, if it didn't find the whole body region, would just take the total field of view count. And they go into calculating the remainder dose, which is a concept in Olinda. Any counts that aren't attributed to particular organs are set as the remainder. Okay, so I think we've got one version of each of the regions that we want here. And now I'm going to click this button, copy void voids. So what it's doing now is it's taking each of those regions and it's copying them across to the other time points. So it knows through string matching on the way in, which is ant and which is post. So it knows to mirror when it has to be able to correctly position those regions. There we go. Okay, so we've done pretty well so far on here. Let's have a look at the next page. Perhaps we want to make a couple of adjustments here. So let's open this one up again. Where has that gone? There it is. So maybe we want to take this this liver region rather, let's say move it so then it can just come with me here, and then I can just place it again. Little pause while it updates its partner there. And you can do that for all of them as well. So if the original lineup didn't work, you can move all the regions. The whole set now come with me as I move my mouse. And then I can just drop it where I want. So in this way, hopefully the outlining of the regions, which tends to be the most tedious part of all of this, is hopefully made slightly less, less tedious. Okay. Going to go on to doing the calculation now. So as I briefly mentioned before, you have a choose from the models available here. So we've got the adult male and female, 15-year-old, 10-year-old, 5-year-old, 1-year-old, and also the pregnancy models too. I will choose the adult female for this one. Choose the isotope. We have almost endless, so many isotopes to choose from here as well. A really nice feature for the true physicists who want to argue with our half-life. You can change that for yourself as well. Here you would enter the activity that was injected. So let's go with this much. And we had a residual of 100 on the injection. There's a nice feature here. So if you didn't have a quantitative spec to put in here and you wanted to use the whole bodies to make your quantitation, you can say if you've managed it, your patient has arrived on the camera with all of the activity that was injected. So if you're trying to do a very fast injection and then image, you can do that as well. The program will just equate the geometric mean counts to the activity that you've said here, minus whatever you've said here if there was any excretion before that first imaging time point. You can put that here as well. There's lots of other details here. It's quite a lot to mention. As Jill touched on, you can do a recovery coefficient if you know it for your regions to try and account for the fact that if a small volume is included, then you don't get the full activity represented in there in the spec. Also here we're doing a scaling of the mass as well. So we know from our specs what the mass is. By the way, these regions were pre-drawn for the demo. They don't automatically appear. Sorry, that wasn't clear. You would have to build these for yourselves, as Lara was showing, either slice by slice or with the interpolation tool. But from those regions, we can take the masses here. So just take the volume of the region, multiply it by 1 gram per centimeter cubed to get the mass. And then the target organ can be scaled by this because that is crucial to the symmetry calculation. It makes a lot of difference. Oh, it's so fast now. Okay, let's continue. So now we're looking at the time activity curves. We have the choice. So we're looking at the left kidney here, got a bi-exponential and exponential fit. Exponential does not look too good for this one, so I'm going to say bi-exponential. You can choose as well to not fit from the first frame, but from the second frame or the third frame if you want. So we're looking here at the fraction of injection activity over the 4 time points that we've got on the whole body. The 2 different lines here represent how the activity from the whole bodies in red here is scaled to match the spec. So that's if you've brought in a quantitative spec, then you can use that information to give the activity and just scale it by the change you see in the whole bodies. So the workflow is to click through the regions that we drew, check that the conductivity curve looks good, choose the fit top if we need to, and then click OK. Now we can pass those calculations, so the integrated area underneath those curves, what makes the residence time, that is passed then to Olinda, and we come out with the dose results. So we've presented in this view here. This can be saved as separate print screens as well. So we've got the uptake curves on logarithmic scale this time. We have the uptakes themselves as a results table. We have the fit parameters for our bi-exponential fit, and the residence time calculation then goes into the dose calculation. So we're looking here at the full doses. So you get everything, because as part of the Olinda model works by saying if you've got some activity in one of the organs, say the liver, you get that cross dose factor to all of the others. Even if it's only very small, you still get a dose for all of the organs that you drew, but only the ones that you did draw will have the self dose factor included, which is normally much the largest contribution to the dose. So looking at our kidneys, we can see got dose contribution from the alpha, beta, and gamma portions of the radionuclide. Total absorbed dose in grey in this column, sorry, in milligray in this column. So we are looking at about 0.9 gray, or 1 gray almost, to the kidneys in this. All right, Steve, I think
that's brilliant. Thank you very much, Helena. And just to confirm, these are all CE marked, correct?
Absolutely,
Yeah.
yes.
And in fact, for our quantitative spect reconstruction of lutetium-177, that was published in a paper recently, whereby the Hermes, especially being an independent system, was more consistent than any other between different
cameras. That's the quantitative reconstruction part. Yes, that's right. There was a really nice multi-center trial, wasn't there, in Holland, I think.
Yeah. So, so thank you very much. If you could put the last slide up.
Okay.
That would be great. Thank you, Helena.
We are going. Let's do it.
That's a nice one as well. Yeah.
Okay. All right. This one, I think. We're getting there, Steve.
Yeah.
This one.
Just to remind everybody, it's a very nice spring evening out there. So, and to thank everybody for attending this virtual user group. Obviously, it's not as nice as a real meeting, but at the moment, I think it's the best anyone can do. So, thanks for attending. Thanks also to all of our speakers on both days. And to everyone that put in a lot of work, especially behind the scenes, including our colleague Jocelyn Palmer, who really coordinated the mail shot efforts and artwork, etc. And for the unsung heroes behind the scenes that are carrying on with the customer support, Marcy, Paolo, Jamie as well. Thanks to those. So I hope it was useful. Please do contact Ben or myself or Helena if you've got any questions about what you've seen, if you'd like to know more. If you'd like to, if we can help provide some of the things that you've seen, if you like the look of them, then please do contact us. We have been recording the event. I just need to check with all the speakers to see if they're happy for us to share that. But once we've done that, anything that we can share, we'll put out in the next few days on our website. We'll send out a note about that. And also we'll send out some evaluation forms as well, together with some requests for the info we'll need to send out any CPD certificates. So with that, I'd just like to say have a great evening, and thank you again. And we'll see you at the BNMS, hopefully, the virtual BNMS next month. Okay, thank you.
Bye, everybody.
Goodbye.
Thank you for coming.